production of Cornell University.
So let's actually talk about this total acidity. It turns out, well, I mean, let's use this slide. It turns out if you think about managing the soils, we can only measure this. But if we look at this whole issue of this cation exchange capacity, we realize that if we want to manage for nutrients, we actually have to manage for this pH as well. It's not just this pH. Okay, so we really, when we think about management, we really have to think about the total acidity. And now this is what we call, this is called the coffee cooler analogy or visualization. What you want to look at here is you want to imagine all these different acidity pools. Okay, and you think about the liquid in the container being that pool of acidity. Now it turns out that the smallest pool of acidity is this active pool. This pool is the smallest pool. It's extremely important, but it's the smallest pool. Wrong way. The size of the cooler, I'll use these two as an example. The size of the cooler represents how much acidity is in that exchangeable or salt replaceable as well as the residual or the structural. Okay? So imagine I have a soil which has a high cation exchange capacity versus a soil that has a low cation exchange capacity. Now, if I have a soil that has high exchange capacity, cation exchange capacity, and it has high base saturation. You guys remember what base saturation, right, is? Base saturation is the percentage of cation exchange capacity that's occupied by bases. All right, so here's my water cooler. Nice big water cooler here. It's got a CEC of 100, okay, and it's got a here's its active pool. Here's another water cooler. This one has a cation exchange capacity of 10. The active acidity pool is the same. Okay? Now base saturation. Let's imagine for whatever reason I have 100% base saturation. So I have in here 100 positively charged cations. They're attached through cation exchange capacity, right? And here I only have 10. Right? So here's my level of pH. Let's imagine this is high pH up here, so 12, and this is 6 down here. Okay? 12 and 6. Does that make sense? Okay, so this is in essence a scale of pH. I start adding protons to this system. What's going to happen to the active pH? It should start dropping, right? So my pH is going to start moving down in both scenarios. But this pool is going to start interacting with the cation exchange sites, right? It's going to start reacting with that exchangeable acidity pool. Now, if I added, this is not the way you do the math, but if I added 6 protons to drop this down, potentially 5 of those protons are going to react. And I now have 95% base sat over here because those bases are now coming out. Okay, and in the process, it's going to take my pH back up. Not to where it was, but it's going to take it back up. Now I do the same thing over here, right? I add 6 cations. No, I add 6 protons. I'm dropping the pH. Those protons go over here to the exchange sites. The bases get knocked off. Let's imagine I take 5 of them off. Okay? So I now have 5% base saturation here. Actually I have 50% base saturation, which means I literally only have 5 bases left, right? Does that make sense? Go.
So the second example was originally it was 10 CEC and 100% base saturation.
100% base saturation. Okay, so both of these guys, when we started, had 100% base saturation. But this guy had a CEC of 100. This one had a CEC of 10. Right? In essence, I exchange 5 sites. I get 5 protons going on to the exchange sites and 5 coming off. Base saturation here is 95%. What's base saturation here? 50%. Okay? Those bases go back into the solution and they raise the pH back up a little bit, right? Question?
Is there a reason that only 5 out of the 6 protons react?
Well, it's exchange reactions, so it's not going to be 100%. Okay? All right. That's what happens. Now, we're now at stage 2. Somewhere down the line, I decide, whatever reason, something happens, more protons go into solution. Right? And that's another 6 go in. Well, what's going to happen? The exact same thing's going to happen again. We're going to have this initial drop of pH. It's going to go a little bit lower this time. We're going to have the exchange. Okay? We're going to lose some bases. And this base saturation now goes down to 90. Right? We've lost 5. Same thing happens here. We have an initial drop. It drops a little bit lower. In this scenario, I put 6 in the system. Okay? We have 5 of them taking over. 1 of them doesn't. Okay? But the 5 bases that are here go into solution. Raise the pH back up. What's my base saturation now? 0. Does that make sense? So in essence, that exchange acidity is buffering, mediating, slowing down, moderating the pH change, right? Scenario number 2. Okay, now scenario number 3 comes along. Another incident. Okay, we add another 6 protons. Right? And here, 6 protons. Again, we have this drop. It goes down a little bit. We have an exchange. We're now at 85% base saturation. pH goes back up a little bit. It's a little bit lower than when it started. But this guy, what happens here? It doesn't have anything to exchange anymore. What's going to happen to the pH? It's going to drop, and it's going to stay down. Because I've just added 6 protons. And yeah, they're going to be exchanging, but they're going to be exchanging for other protons. Does that make sense to everybody? Okay. So with this graph, I've taken a number of steps here. In fact, I've basically presented half the lecture right in this graph. Okay? But the take-home point with this slide is you have to consider the entire acidity when you start thinking about basically managing. Because we can take this scenario and throw it the totally other way. What happens if I start adding bases? What's going to happen? Okay, imagine that I add 10 bases, 10 charges, 10 positive charges that are bases. Okay, in this scenario, if it's not going to be 100%, but in this scenario, if I add 10, I'm going to basically put this right back up to 95%, base saturation to 95. I'm going to be raising the pH, and then it's going to drop back down, but it's not going to drop down as low as it was. Does that make sense? In this scenario, what's going to happen? If I add 10, and granted, we're not going to get 100% exchange, but if I add 10, we're now back up to 100% base saturation. My pH is going to bounce back up, right? But what happens again? This guy is back at 95. What happens if I add 5 bases again? And I'm going to bring this guy back up all the way to 100% base saturation. What's going to happen in this scenario, though? Where are those bases going? They can't go there. If they're not taken up by the plant, what's going to happen to them? They're going to be leached from the system. So not only have we talked about pH, we're also starting to talk about fertilizer. I need to know what my cation exchange capacity is. I need to know what my total pool of acidity is so that I can, in fact, manage for these management scenarios. Make sense? I use these, there's 2 slides here, and I use them as segues, and it's really sort of the segue. What is this relationship between pH and exchangeable cations? Okay, because you got to think about this. What happens to the pH when? What happens to the CEC when pHs change? Now I have a permanent charge associated with my cation exchange capacity, but I also have a pH dependent charge, right? So that pool of base saturation is going to change based on the pH, right? In this scenario, we're basically assuming it was a permanent charge. But what happens if that CEC is not static? It changes based on what my pH is. And so right here, this graph basically looks at percent of maximum cation exchange capacity. Okay, this is how much you can hold. Okay, and this is soil pH. Okay, and this is a mineral soil, where this line right here represents, or I should say everything below that line basically represents permanent charge, and everything above that line basically represents pH-dependent charge. As the soil pH increases, my effective cation exchange capacity also increases, which means that pool is going to get larger. That exchangeable pool is going to get larger, right? As the pH goes up, as the pH goes down, that effective capacity is going to go down. Now, what happens when I start adding organic material in here? Organic material has a much, much larger pH-dependent charge associated with it. Here's the permanent charge right here, everything below that. Everything above that is pH-dependent. So as my pH increases, my effective cation exchange capacity increases, hugely affecting those pools. Okay, questions? All right. This is just a slide I threw in here to you guys to remind us of what base saturation is. Base saturation is just that measurement of the cation exchange capacity that's occupied by bases, the percentage.
This has been a production of Cornell University, on the web at cornell.edu.